Okay, so today it seems I am not going to be able to make something and not have the recording cut out. So there's that. And I am not about to go through all of these and rewrite them because that's what took the majority of the time last time. And so I'm just going to briefly go through these. So this is in liters per minute right here. This is the rate of flow in. This is the concentration in. Or this is actually the rate of flow in general because it's the same throughout. And then this is 1 mole per liter here. This next one is in Kelvin. All these temperatures are going to be in Kelvin. This is time, so this is in minutes. I'm just going to start here. So anything with T, big T is kelvins. And then this volume is in liters. This density is in grams per liter. This heat capacity is in joules per gram Kelvin. I have my board here that tells me all of this. Enthalpy of reaction is joules per mole. Activation energy, also Kelvin. K naught, which is the rate of collisions inside for the reaction, is in inverse minutes. UA right here is in joules per minute Kelvin, and this concentration is also in moles per liter, and I am done with that. So I got all those down the last time, and I think I also explained these. These are, nothing is new here, so there's that. And then, okay, so the next thing we need to do is define the right-hand side of the equation. And that's going to be in terms of time and a vector v. And I need a colon. Yeah. And so it is going to be CA, and then T is equal to this V. And that, no, we want regular little. Okay, that was just taking too long. And then I messed this up in the last video. I said it was this is the K equation, so K is equal to K naught times numpy exponential, which is just e to the whatever. And it's not actually the activation energy over temperature. It's negative activation and energy over temperature. So I got that wrong. And then this is going to return an array of these two values right here. So that is the differential equations we did last time. So that is Q over V times CAN minus CA minus K times CA, comma, let's just press a space. And then this is going to be another Q over V, T in minus T. And then this is where it gets fun, is plus the enthalpy, which is negative. It's negative, but the negative activation energy takes care of it here. So it's weird. It works out. I tried having it negative last time when I did the recording, and that didn't work. And I found out that having it negative in here is not what you need. I think the equation already accounts for it. So HR times K times concentration divided by, and this is another mistake I made last time, is I did not divide by this initially, divided by our density, this is not a capital P, times, this is a rho, times capacity, minus UA times T minus TC naught divided by rho VC. Got that done. The next bit of code is solve IVP. So our solution is equal to solve IVP. And that is going to be our right function. Bounds of integration are Ti to Tf. The initial conditions are Ca naught and T naught. The method is Radau, I don't know how that's pronounced. And then finally, our dense output is equal to true. And to make that blue, I'm not going to be a doofus and put parentheses around it, because that does not work. Yep, and it works now. Okay, and the next thing we need to do is make a t-plot, which is equal to numpy linspace, and that is ti, or initial time to final time, and 500 data plots. And then we want to make, I believe it's CA, and then T is equal to solution of, or a solution in terms of this TP. That is not it. Oh, I need the dot sol because that's the value that we want, and that rips that value. No, I pressed space. Okay, there we go. That works now. Come on, give me another piece of code. There we go. Okay, and then the last thing to do is figure is equal to make subplots, and this will be a nice refresher. Something new to put in these parentheses is columns is equal to 2 and rows is equal to 1. So we have that. And I did not feel like writing all that out, so I just copied and pasted that from the last time that I did it. So I decided to take the liberty to name it, and then I put this, you'll see what I mean. You'll see why it's rows and columns real quick. If this, it works. Okay. Looks like second time is the charm for this. Let me make sure I'm still recording. I am still recording, thankfully. Okay, and so the next part of this homework, which is outlined right here, this is where I got all these values from, is to, well, I can't highlight it, but so I'm going to drop the temperature to 290K and see what happens, and then I'm going to raise it to 305K and see why chemical engineers get paid so much. All right, so I believe the thing to do is change this cooling temperature down to 290 and see what happens when you play with it. Okay, so you'll notice that I'll notice there's not that initial drop, so it goes straight down to the temperature and it gets to, I believe, just like 312. Okay, so it gets to about maybe the same temperature and about the same concentration that you want, and it just goes there a little faster, I think. Now, I guess we can go back to 300 just to see the difference a little more clearly, since I kind of went through that at a bad, in a bad way. Yeah, it goes to its set point sooner. It does not have this little divot in, but it still it goes to 324. And it goes to 0.9 something. Okay, good to know. So that's a little weird. It's gonna have obviously it's gonna have a lower temperature because you're having a lower cool temperature. And now, here's the fun part. 305 kelvins. Yeah. This is what figured. And this is why 5 kelvins makes a difference. This is why you got to figure this stuff out. Hopefully not the hard way, but hopefully by... I don't know what I did there. Rerun that. But you'll notice that I'm not going to point at the screen because that's not going to help you guys. So at 2, or rather like just after 2, this is, the concentration's really high. So as the concentration is high, the temperature is lower. And as the temperature is higher, the concentration is at its lowest. Well, aside from this right here. So this is what causes explosions. Because you'll notice in like less than 30 seconds, it goes all the way from 350 Kelvin to 400 Kelvin, which is, I'm not going to try to do the Fahrenheit to that, but that is a lot of temperature difference, and this is how explosions occur with exothermic reactions. I'm not sure why this is all wavy like, but it's not supposed to make sense, and that's also why this is like overflow encountered, is because this is what happens. So yeah, that's no, that is what happens when you mess with exothermic reactions and don't know what you're doing.